That's me. So, this is Peter Sagari from Terena, and I'm chairing this session, which is about optical networking and beyond. We're gonna have 3 speakers from industry, 2 from ADVA, and 1 from Siena. That's the way how I can pronounce this. And these are all about some kind of optical networking. So we're not going to write any exam at the end of the session, so you can come and use the front seats, and maybe we can have some good discussion after the talks. And I'd like to introduce the first speaker, Veistunen from ADVA, and he's going to talk about packet and optical network integration.
Okay, good morning. Thank you all for coming. I know it's early on the last day here, so it's nice to see there's a few faces out there in any event. What I'll be talking about here today is essentially when it comes to bringing optical networks into the realm of packet networks, how do these two very different worlds come together? And looking at it primarily from a control plane perspective. You'll be hearing, I'm sure, a lot more about optics and hardware here later on. So the basic thing that we're recognizing, I think most are recognizing, is the LAN is essentially converging into 2 layers. There's an optical layer, which is providing usually end-to-end transport between packet devices, which are then providing the service layer. And so these 2 things are, in many ways, this is a good thing to say that we're reducing the number of layers in networks and hence the complexity of them. But we do have to recognize also that these 2 layers are quite different. That a packet network, of course, is a service layer. It's connecting IP routers or MPLS LSRs or what have you. And it's providing essentially a packet-oriented service to cloud, CDNs, whatever it is. But there is, in any event, a packet technology, a packet focus, and a packet operational practice, which, of course, is different from an optical network. An optical network is all about WDM transport, et cetera. It's usually point-to-point, wavelength services, et cetera, primarily there to support the packet layer. And it has its own focus, its own operational practice. So the challenge is, at least from a control perspective, how do we create some sort of a structure that makes these 2 very different worlds come together? So we talk about layers, and it's probably a reasonable thing to go through what we're talking about when we talk of layers. Here we're talking about there is a packet layer, there is an optical layer, but in reality, one can think of these in terms of client and server. There is a server layer network, which is down here, providing some sort of bearer channel capability up into some client layer network. So in this picture here, the client is the packet layer, the server layer is the optical layer. If you start out with a packet layer that has no optical provisioning done yet in it, you can think in terms of the client layer topology. Really, there's no topology there. Okay, yes, there's a bunch of fibers connecting everything together, but from a packet switching perspective, if you're trying to switch packets through your network, until there's something down there in that server layer providing the connectivity, you really don't have any topology at all. And so up here in this client layer, you see there's a bunch of different nodes, but they're not really connected by anything. So how do we connect those together? Well, we start provisioning wavelengths. If you have an optical layer that's providing capability into your packet layer, the way that you start creating topology or creating connectivity amongst those different client layer entities is by bringing up wavelengths. And so here we're just starting to provision these connections down in our server layer, which is again our optical layer. Those connections are wavelengths. As we bring up those wavelengths, it now is injecting or creating topology, creating connectivity between the different client layer entities, which in this case are likely IP routers. The purpose of doing this, of course, is at some point you want to have created enough topology in your client layer, in the packet layer, in order to actually do service provisioning at that layer as well, which is what we want to get to here. So this is a very traditional IT2-driven layering concept that says you have certain layer of services that are being provided as a service to some higher level, which then that higher layer is using it for its own provisioning purposes. Now, you recognize, though, an aspect of this picture says that before I can do anything in my client layer, I have to have gone and provisioned all of my server layer stuff, which means I have to have created all my wavelengths and prepared all my topology before I can do anything within the client. And that's a little bit unfortunate, right? Why would you want to actually have to nail up all of your optics in order to be able to do something interesting in your client layer? So we'd like to provide tools to get around that. And this is where the virtual network topology concept comes in. What we're talking about here is essentially creating these abstract representations of real networks that can be injected into a certain layer network in order to be able to do things prior to the underlying support actually being there. And I'm waving my hands here, but we'll get to a picture in a moment. But the purpose here really is we want to be able to abstract the capabilities of one layer and present that to another layer in a sense that that layer can then start to use it. This provides adaptation between the layers so that now we can start coordinating between the two. And it also then allows us to do even things like activation, to say that when I do operations within a higher layer, I'm going to use that virtual topology as a way of activating that underlying server layer. So rather than me waving my hands, let's get to a picture. We start out with the same thing we had before, but now you notice up in the upper right there, there's a planning box. And what that says is someone's going to sit down and say, I want to have a certain connectivity across my client network. And they'll sit down and decide essentially which IP routers do I want to connect up. And by using a virtual topology, we'll essentially inject into that client layer topology a set of links, a set of traffic engineering capabilities that the client layer then, in this case the packet routers, know exists. Okay, now notice that nothing's gone on in the server layer yet. All we have is a set of essentially information that can be processed by applications running in the client layer to say, okay, now I can actually go do things. So given I have enough topology that's up in my client layer, I can now go and compute a path. But of course, as I compute the path, there's actually no server layer yet that's been provisioned underneath it. So how do I solve that problem? Well, what it says is that as I go and start actually activating my client layer, there's some interlayer coordination that's going on between these two. That says the network element that is providing the adaptation between the two layers, which in this case is the optical device, notices that when it receives a request at the client layer, it can then say, okay, this client thing that I'm getting a request for actually requires that there be some server layer connectivity brought up in order to allow that client to continue. And so in this case, a client has gone and signaled the server layer notices, brings up the wavelength that's required in order to realize that piece of topology. Notice that the dotted line became a solid line. That means that a virtual link just became a physical link. And then this proceeds its way through the network. So at each point along the way, as I signal through my client layer, I'm successively activating the underlying server layer components that are needed in order to be able to actually realize this path. The benefit that we get out of this, of course, is that you don't now have to have your optical layer all nailed up. Okay? You can go in and say, I have a certain connectivity requirement across my client layer amongst my IP routers, and then I can go have that actually activated in the server layer, in the optics, on demand, effectively, when I actually use that client layer topology, rather than having to nail it all up to start with. This starts to inject some degree of dynamism, some degree of adaptation in the optical layer, in the server layer in this case, that up to this point likely wasn't there. So the thing that enables this is this notion of a virtual link. You see each one of those dotted lines I had up there in that client layer is essentially, it's a potential connectivity. As far as the IP router sees, it's a connection between these 2 points. But from the server layer, it's a potential. It's essentially a promise on the part of the underlying optics to say, if you ask me for this type of connectivity, I will give it to you. The resources that are necessary to make that link actually operate aren't committed, okay, until that link is actually used. But they are essentially a promise, as I was saying, to say that if I'm asked to cause this link to come into being, I will then go into my optical network and bring up the appropriate wavelength. And what this allows us to do then is to do virtualization of networks. The technology that sits behind this is a thing that's called a GMPLS overlay, which some of you may be familiar with. There is an RFC that was issued, this was back in 2004, I think, something like that, that essentially defined what an overlay model would look like if you're operating within a GMPLS network. This was back, 2005 rather. This was put out back at that time frame. There's been a lot of experience since that time about making these actually work inside of a real network. And so there is now actually a draft out there which is working its way through the process to try to codify the actual operational behavior of what one of these overlay networks would look like. And you can use that as a reference if you're interested in finding out what the best current practice is as far as using an overlay. But this is really what we're talking about as a GMPLS overlay network. But let's us get to these sorts of scenarios. So say we have a user. The way you can read this picture is the upper level is what the packet devices see, the bottom layer is what the optical devices see. So there's some optical network that's being presented to the packet network. And again, in this case, there's no topology yet, so there's no connectivity amongst the packet devices. But a user can say, okay, I'm going to say this user number 1 has these 3 links, the green that you see up there. Okay, that's the topology that's being injected into the client layer to say, if this user comes along and wants to create some service amongst his packet routers, this is the topology that he sees. There's some transformation that goes on, and effectively it says, for those sets of links that I'm making available to him up in the packet layer, these are the wavelengths that I need to be able to bring up underneath it. And that's what the green lines down in the bottom part are. We can go to a second user and say, for this kind of user, I'm going to present an entirely different topology. Okay, in this case, it's going to be the red links that I've got up here. Okay, again, those things are what that user sees, which may be different from what the previous user sees. And again, when it comes time to actually realize that connectivity, these are the wavelengths that I'll have to bring up. And notice the way that the wavelengths are routed down here may be completely disjoint from the way that they're presented upstairs. This is entirely fine because we're just providing connectivity between routers. We're not actually indicating what the physical layer stuff is that's going on in order to realize that link. And again, we can go to a third user. So this third user may see an entirely different topology. Okay, again, based on the application, what it is that that user wants to do. This is the topology that's being provided to that user. And again, here are the wavelengths that we would need to provide in order to satisfy that topology. So all that's by way of saying, now I can get to link activation. I can now get to the point to say each one of those users may come along and say, now I want to have connectivity across this region. So we'll start out with user number 1. He starts down here. He's doing his packet LSPs amongst his packet devices and then reaches the edge of an optical cloud. Okay. Something then has to occur. In this case, user number 1, I think, is the green, if I remember correctly. So there is a link across the optical region, which you can see. There's a optical device at the end that notices, okay, there's an adaptation that has to occur. I have to go from a packet down into an optics. And so it takes care of that problem, brings up the wavelength. Okay, this has now made that connectivity across that region accessible, which then allows that LSP to continue. This is then a way that the user, as far as he's concerned, he or she is concerned, they're just operating their packet routers. They're just turning up LSPs. They're not really even seeing what's going on down in the optics. But the optics is taking care of ensuring that the underlying channel that's needed is actually brought up and available. So this can proceed again for each one of these different users. Again, when they reach the edge of the optical region, the overlay notices that there's an adaptation that has to occur, brings up the appropriate wavelength, and then allows the LSP to continue. And again, we can do this for the rest of our users as well. So this is a way of saying that there's an adaptation and a coordination that's going on between these different layers. And what used to be done by people sitting down at keyboards now can be handled entirely by a control plane operation that's aware of what's going on within these different layers. So what's the benefit of this? Why would I be interested in doing virtual links in this way? Well, one of the aspects is when there's diversity. If you're concerned about, for example, up at your packet layer, not only am I trying to hook up my routers, but I also want to ensure that I can run some higher level applications, say some sort of protection related operation that then requires not only do I have connectivity, but that those connectivity satisfy some diversity characteristic. Well, if you have a fully encapsulated region, you may not have an understanding of what the diversity is. Whereas in this case, when you have links, those links that are being provided up into the client layer can also be annotated with information that identifies what their diversity is. In other words, are those two links following the same physical path or not? And in this case, what happens is at the server layer, there may be some noticing, as we see over here on the left, that the green and the yellow are actually sharing part of the physical topology. So the way that that's indicated up to the client is through use of an SRLG. And hopefully folks are familiar with what an SRLG is. But in any event, it's a way of identifying when any number of links that may exist in a network actually share fate. If you didn't have these individual links exposed as part of the topology to the user, they wouldn't be able to determine whether there is in fact a diversity problem there or not. So this is part of the motivation of why you go about using a link-based network virtualization mechanism. So we sometimes get questions too to say, how does this intersect with SDN? Okay, SDN's a big term of art now within the community, and so if you're trying to do network virtualization, but you're coming at it more from a software-defined networking approach, how would you do this, again, when you have a network which is merging together packets and optics? So I'm not going to go into the details of SDN. I'm pretty sure that most folks are up to speed on it. But in any event, there is this OpenFlow concept out there which is being used primarily for dealing with layer 2, layer 3 networks, and identifies how do you create flows essentially through those networks. So if you've got a bunch of, again, layer 2, layer 3 devices, but there's an optical network in the middle, how do you bring these two things together, and how do you create a virtual overall topology out of that? Well, we have to think a little bit about, again, back to what the differences are between these different layers. Within, the great thing about packet networks is they're digital, right? Everything is very nice and clean. They're ones and zeros. You can bring in a packet on any interface and take it out any other interface. Switches are very orthogonal. Every path is feasible. It's all about connectivity. Good stuff. Optics, of course, not quite that simple. Optical networks are basically analog. At the end of the day, they are switch fabrics, but those switch fabrics are very non-orthogonal, which is sort of an interesting way of expressing it. But in any event, you can have a bunch of paths in an optical network which are topologically possible, but actually are not optically feasible. And all of that kind of complexity of how do you create a path within an optical network is very hard to express out through a fairly simple interface like the interface available through OpenFlow. So we need some sort of a practical approach for bringing these two things together. So just as a way of emphasizing that point, if you're actually trying to create a flow across an element in an optical network, this is all the stuff you have to take into account, and this is actually just a summarization of the actual detail. There's all sorts of crazy things that have to be included in your determination of what to provision, and then also how to calculate the resulting path in order to be sure you come up with something that's actually feasible. So, what's our different approaches? So, if we've got an optical network and we want to integrate it with a packet SDN, again, we recognize these SDNs are primarily interested in layer 2, layer 3. Optics are usually seen as just a point-to-point communication or point-to-point connection between different L2, L3 domains. So, what is our approach here? Well, so we can think of these things in terms of domains. All of these different things, we have an optical domain, we have an L2 domain, we have an L3 domain, and somehow these things need to come together. So what is a characteristic of a domain? So a domain essentially represents a single region of control, administration or control, I should say, and they have various attributes. Okay, a domain is connected to other things, so it has attachment points, and these are ports. They have adaptation functions. If I'm going from this domain to that domain, packet to optical, there's some action that has to be required in order to be able to do that adaptation. And then there's connectivity across the domain, okay, which can map to a flow. If anyone's familiar with SDN, some of this should start to sound familiar, okay? Each one of those terms that I've just identified, port, action set, and flow, those things are all primitives within the existing SDN architecture. Which says that then, okay, rather than using a virtual link, if we recognize that there's a domain and an L2 switch, or an L3 router for that matter, is just a highly localized domain. It's a domain within a single physical device. OpenFlow usually assumes this controller-device ratio of 1:1. But instead, how about we think about a controller, an OpenFlow controller, an SDN controller, to domain ratio of 1:1. So what does that look like? Essentially looks like something like this. All right. In this case, we have an SDN set up, a bunch of layer 3 routers in this case, each one with an appropriate domain controller for their SDN application. And then we create one big switch in the middle. And that switch also has some sort of an OpenFlow adapter as well, or an OpenFlow controller. You can use the same sort of concept that I was just outlining with the links, but use it in a similar way here. We've got a user out here that talks to his SDN app, says, okay, I want to create some connectivity across this. The SDN app does what it does. It goes to the first part of the path, says, okay, set that up. It goes to the second part, which is our switch. Okay, our switch in this case is really just a representation of the optical network that's underneath it. So what happens is essentially it's a translator. The OpenFlow comes in, says make this flow, make this entry in your flow table for this region of the network. That turns around and actually activates the optical network to bring up the appropriate wavelength. And then it proceeds on to do the rest of this connection. Okay, this is another way of looking at how do you go about and create connectivity across an optical region, but activating it, in this case, from an SDN rather than from some control plane driven solution. And this proceeds on, as I did before, with the link approach, which is to say, again, user 2 comes in, says, now I want to create connectivity. He does his initial connection, talks to the switch in the middle, which does the appropriate translation to bring up the wave, and then talks to the endpoint in order to make the rest of that connection. And again, you can see where this is going. User number 3, talking to a different set of elements, starts out as connection, talks to his element in the middle, sets up the flow table, which causes the wavelength to come up, and then the rest of the path is produced. So another take on this whole idea, again, our purpose here is to try to figure out how do we bring packet and optic together? How do we bring these two technologies together, recognizing that there are some that are running end-to-end control plane, there are others that are investigating SDN. There's clearly approaches that will work in both areas. So some observations about these two. There are virtual links. In the case of the virtual link, you get more topology information. You have the option to essentially inject as much topology, as many links as you want to, up into the client layer to give that client the degree of control that it wants. There was actually a very interesting presentation earlier in the week that was struggling with this, to say, how much topology do you end up exposing to your packet layer? And it's not clear what the right number or what the right amount of that is. So one of the virtues of the virtual link is that you can use just the number of links that you want to have or make available to that client, and no more and no less. So you get into this kind of just enough topology concept to say this is what I want to actually provide to my users. Also then it gives the packet layer some more direct control over what that optic layer is doing. The finer grain your links get effectively in your client layer, the more control they have over the server layer. Now, switches on the other hand, they're very simple. It's a very simple concept to grasp. To say I've got a switch out there, it may represent 1, 10, 15, 50 elements, doesn't really matter. It's just one big switch, ports on one side, ports on the other, make flows across it. As some of you may know, there's even whole companies that have been named after this idea. So gives you some idea of where the thoughts are. It does encapsulate all the complexity. Again, you're not having to deal with all of the analog aspects of the optical network. But it does also have limited topological control, which means that the amount of available control that your users have up in the client layer is relatively small when you're operating down there, because you're encapsulating this entire region in just one switch, and all you have is control over the flow tables. So there isn't one right answer, is the basic message. There's different techniques, different ways of going at this problem, and it's essentially look at the problem that you have in front of you, use the right set of tools in order to meet that application. So, kind of a whirlwind tour, but in any event, this is a couple of different mechanisms that are existing today that will allow you to take an optical network of whatever complexity it might be, make it available up into your packet layer network, and then exert some degree of control over that network so that you're not having to spend a lot of time dealing with the complexities of the underlying optics. So, I think I'll leave it there. Happy to take any questions that you might have.
So, we have a mic here. So, do you have any questions to us? Yes, one up there.
5 minutes.
Hi. Thank you for the presentation. This was very interesting. I'm wondering though that, and I didn't get this from the presentation. Is the if you're triggering the optical layer to make a circuit, is that path calculated dynamically, or is this predefined?
It can be either. In the case of the virtual link case that we're talking about, in the implementation that's in the ADVA devices, it can actually be either. You can just identify the two endpoints to say I want to go from A to Z, and then at the time that the link is activated, the control plane goes and uses whatever topology data that it has available and actually computes the path at that time. However, if the user decides, well, I really have a very good intuition or desire for that particular path to be realized in precisely this way, the user at the time that they're identifying the endpoints can also specify the path it's supposed to take. So either one of those either one of those ways of operating are possible. It's a matter of what the application wants.
Okay, and you've identified that you've made a sort of OpenFlow-like interface for the optical network. Have you considered making an NSI interface for the optical network?
Yeah, it's a reasonable question. We haven't gotten to NSI yet. We've been looking at the various different things that are out there as targets for doing integration of optics with packet layer. Clearly, the GMPLS approach is something that's been going on for a long time. The SDN with OpenFlow, of course, is getting a lot of attention, and so getting a lot of ours as well. NSI, we're not quite in that realm yet. I'd be interested to know if you have an application out there that actually would see that as being a beneficial thing, because I would be interested to know what the demand for that would be, and then we could put together something perhaps that would address that area as well. So maybe we can talk afterwards. You can tell me what your thought is.
So my question is related to not just the optical layer, not just the analog domain, but and it's sort of, let's say, ADVA specific. I know that you've got some carrier Ethernet transponders and that sort of stuff. Is your implementation of the Ethernet layer making use of these virtual link technologies already?
Yeah.
To deliver circuits on the layer 2 level?
Sure. In fact, yes, is the short answer. In fact, within the ADVA devices, there's an Ethernet layer, there's a OTN layer, there's an optical layer. Each one of those layers is all supported by the virtual link concept that I outlined. So I was concentrating primarily on packet optical because this is where we see a lot of things going. But if you have an Ethernet layer that's in the middle, or you have a OTN layer in the middle, all the same concepts still apply. Fair enough?
So, in most of your presentation, you were talking about this as the abstraction layers and the client-server mapping being about interfacing from a user-client application towards a physical infrastructure. Are you also considering the same abstraction methods as a way to handle the exposure and exporting between multiple organizations in a multi-domain environment? And then do you envision multiple layers of this client-to-server mapping? And is that going to affect how the efficiency of this type of mapping? And then how do you see yourself handling that?
Yeah. So there's two aspects of that. Yes, I think to the first question, we certainly do see that this idea of exposing topology does apply not only between a network and a user, but also a network and another network. So the same sort of concept would apply to say that if I'm organization A and I'm talking to organization B, I may use this mechanism to only expose certain parts of my topology to that other organization. So no worries there. The other is, as far as how many layers to go up there, there's no limit here to say that it can only be 2 layers. It can go kind of as deep as you want to go into the rabbit hole. At some point you get to a point of operational complexity. Maybe you don't want to go there. But as far as the technology, yeah, we can go from an optical layer to a TDM layer to an Ethernet layer to a packet layer to on and on and on and on.
also the multiple layering thing can simply be because of many organizations, so you have mappings and mappings and mappings because of your re-exporting infrastructure.
Sure. Yeah.
Thank you.
Thank you very much. Thank you very much for your questions, and thank you again for this talk. We have a next speaker also from ADVA. He's Klaus Grobe, and he's going to talk about software-defined optics a little bit more.
Thank you. Morning, everybody. Now for something completely different. It's not software-defined networks, it's software-defined optics, which is some flexibility in the optical layer, and I'm really restricting myself to optical layer aspects, to possibly next generation ultra high-speed transport for research networks, for data center connectivities. So a bit of outview what may come beyond Coherent 100 gig, but I will start with 1 or 2 slides on Coherent gig just as a reminder, then the extension towards what may come next, and quick outview on software-defined optics and their capabilities. So just as a reminder, the block diagram of a Coherent 100 gigabit system, the OIF standard, duly polarized QPSK, the modulation format, whatever that means. I mean, there were several talks the last years on this topic, so I guess you all know what I'm talking about. This is the block diagram of one such system. Unfortunately, I don't know if I have a laser pointer here. That would be great, but okay, you can see, well, the main thing on the left-hand side, it is a dual polarization transmitter, and each polarization plane uses a complex IQ modulator that is necessary already for the QPSK, where in fact QPSK is the simplest complex modulation scheme. On the other hand, it's not only the simplest, it's also the best with regard to the SNR requirements. So likely we will not be able to top this in terms of maximum achievable reach anymore. And on the right-hand side, you see these red highlighted blocks, which is the core of the digital receiver. Yeah, there it is. Okay, so we analog digital convert the 4 or 8 streams that come out of the optical hybrid, and the coherent optical front end, and these are then processed in a big DSP. And I will come back to a very similar block diagram towards the end of my talk. Because this is already a very good basis. It obviously looks completely different as old times 10 gig on-off key systems, and we'll see this further on. And it has certain capabilities. It has, for example, a pretty good, as compared to old times technology, spectral efficiency, and clearly we have to increase that one in the future because of the exponential increase of bandwidth. It has certain reach, which is pretty good, and there, by the way, first problems come because the maximum reach on uncompensated links is not the same than on compensated old links, and it depends on many parameters. As Wes said, this is analog technology. And let's see, okay, problems number 1, which indicates there's more than just one problem. If we in the next 5-8 years or so have to massively increase bandwidth, and I think there was on OFC 2 years or 3 years ago, there was a talk by Bob Metcalfe who said, well, within 10 or so years we will need terabit Ethernet and that meant terabit Ethernet per channel, per wavelength channel. He was still talking about 100 wavelengths or maybe 200 or something. That would mean we have to drastically increase the total capacity of the fibers. And these two little diagrams shall indicate that will become very tricky, because let's start with this one. This, by the way, is now being known as the nonlinear Shannon capacity limit of the fiber. What does it mean if I want to increase my fiber capacity? That is, if I want to increase spectral efficiency, I have to increase SNR. That simply means I have to spend more power for the payload. And then I could theoretically write close to this curve here, because I would be enabled to use higher and higher order QAM mechanisms. I would theoretically go exactly the way I did with old-time modems, and I do with in some other areas. So I would go from QPSK to 16 QAM to 64 QAM to 1024 QAM, what have you. Unfortunately, I would have to spend more power, and that doesn't work. Why does it not work? Well, simply because the fiber, as almost any other natural system, is a nonlinear system. There are no real linear systems around. So the fiber is what we call weakly nonlinear. Unfortunately, it's not that weak. What does it say if I try to increase power in order to increase signal to noise ratio? I will face a whole bunch of nonlinear effects, which I'm sure you all know, self-phase modulation, etc. And these, in the end, will destroy my transmission. And so far, it seems there is no way around. Of course, now many people are talking about nonlinear mitigation. Unfortunately, it requires effort on the one hand side, and the gain is pretty little. Even with very massively demanding, in terms of DSP, etc., demanding mechanism, you may gain a dB or so. So it seems with standard fiber, we may sooner or later come to an end with regard to capacity. What about added coding, advanced FAC, and what have we heard during this conference? Very similar game with the FAC mechanisms that are implemented today. We are already pretty close within Shannon reach. So don't expect to see a useful, feasible FAC that gives you 15 dB in a couple of years. That will not be possible. It would add an awful amount of overhead, and you would again start riding these curves. Unfortunately, that is not everything, because our channels have to traverse networks, and in these networks there are filters, normally in ROADMs, etc. And if you look at a single filter, it may have a certain passband shape, and if you look at your modulation schemes, okay, we have DP-QPSK these days, they may or may not fit well into these passbands. Normally they do. But as you all know, if you have cascade filters, if I look at a series of 4 or 8 or 10, the passband narrows down. So effectively, this poses another requirement on sort of a spectral efficiency. We need narrow band signals or signal shapes that can go through a certain number of filters. Here, by the way, the effect is shown how the passband narrows down with the number of filters you cascade in your network. Okay, I will come back to these two problems, or 3 or 4 problems, in a minute. Now, a quick slide on the next generation ultra high speed in data centers and consequently in your networks. Why 400 gig, why 1 terabit? I already mentioned it, simply because of exponential bandwidth growth, and it will come sooner as we expect, I think. And in effect, it is not about decreasing the number of interfaces. It is not about decreasing the number of wavelengths. this will remain. We will, in 10 years or so, I don't know, we will likely talk an increased number of wavelengths, possibly an increased number of interfaces, but then running not 1 gig or 10 gig, but running 100 gig or even more. So that is mainly the driver, and we do see it certainly in data centers. Think about the actual generation of high-speed InfiniBand interfaces. These already do support 120 gigabit, if not more. I don't know if they are already at 240 or so. And then in transport between data centers, we do see a huge diversity regarding distances, and typically in networks, and we also see inverse proportion between the bandwidth that is required and the reach. That is typically the shorter, the higher the bandwidth requirement is, the shorter the reach is. It's not always the case. I know many of you like to transmit huge bandwidths from one point of the Earth to the other, downside under or wheresoever. But this can often at least be seen, and it is part of the answer and the capability of software-defined optics. Now, what is software-defined optics? It's the software-based configuration or implementation of operating functions. For example, the software-based implementation of a modulation scheme, of how you put your sub-carriers together, etc. Because with 400 gig, starting with 400 gig, we will see very, very likely optical transport based on more than one carrier, based on more than one laser line or whatever you call it. It's not necessarily about OFDM, by the way, but it is certainly about more than one optical carrier. And yeah, here's some examples. I think I showed this picture last year already. So if everything was software based and flexible, we may jump from QPSK to 8, you should say 8 QAM here. This is 8 PSK in fact, but if you want to go for an 8 array modulation scheme, it's likely to be 8 QAM to 16 QAM, what have you, and all of these are duly polarized. That is for sure. And then already, I will come back to this one here in the almost in the middle. That is something strange. And what stands QPR for? It's quadrature partial response. So I guess that's my personal guess. We will see a partial response coming back. Why? First, a quick slide on effects of this flexibility. So if I now can switch from, where is it, QPSK to 16 QAM and something else here, PS QPSK would be polarization switched QPSK. So what I do today is I independently modulate both polarization planes. Why? Is possibly a good question. I could combine them and in a combined manner jump between polarizations and constellation points that might in fact give me a dB negative penalty, so an advantage. But in effect, and that's what this diagram shall say, is we will not be able to really massively increase spectral efficiency. That means increase fiber capacity and stay at the same maximum reach, because what is shown here is well, penalties, and penalties translate to negative reach requirement. In other words, if it comes to the highest reach, ultra long haul, it is very, very likely we stay with DPQPSK because it is the best we can do. But what we also can do is we can switch to higher order QAM or something and put within the same analog bandwidth more payload. And consequently, we would see a penalty, which simply means I could transport higher payload, higher capacity over shorter distances. This is exactly this inverse proportional behavior of reach and capacity that I talked about. So it would fit many applications, certainly not all of them, but many. Yeah, let me come back to partial response. I already showed this diagram with the filter passband and the bandwidth of analog signals. That brought some people back to the idea, by the way, invented in the early 1960s, of partial response, which is sort of a intentional correlation between successive bits. So I put my bit streams into a very simple delay filter, and by doing so I correlate between the successive bits. That sounds in first place weird, because I also need to detect at the receive end now successive bit sequences instead of single bits. That would not be possible anymore. And that means I need MLSE receivers, but that is no problem. But it gives me something in the analog domain. It gives me quite a dramatic gain in analog bandwidth. So I get massively narrower at very reasonable penalties. This is shown here. What is shown here is if I, for say 400 gig, have to go on a 4 subcarrier scheme. That is, I have to use 4 laser lines, no matter how I organize these. The question is how tightly can I squeeze them together? And that is shown here with QPSK, the standard that would be used for 400 gig. So think about 4 carriers of DP-QPSK being tightly pushed together. And then same thing, same capacity for the partial response equivalent. And what is shown here, the partial response equivalent, this one here, comes with a certain penalty, but the penalty is less than 1 dB. But if then I try to squeeze the subcarriers tighter together as given by their baud rate, I immediately see a very heavy penalty for QPSK, whereas there is still quite a relaxed domain for the partial response. That is simply because it is narrower in its analog bandwidth. And I can squeeze them together as tightly as approximately 0.85, where normally all the multi-carrier experiments today are not being done at 1.00, but between 1.05 and 1.1. So I gain approximately 20% over what is being done today for approximately 1 dB penalty. This is huge gain. And it does work. This is a simulated experiment we showed at OFC. 4 subcarriers carrying 120 gigabit each, so that would be a 400 gigabit Ethernet signal put on 4 carriers or 4 wavelengths, 4 laser lines, whatever you call it, being transported in one analog super channel of 125 gigahertz analog bandwidth. So that would have to be provided by sort of a flex grid ROADM or gridless ROADM, or you know what I'm talking about. It does work for QPSK in a very narrow range of the subcarrier spacing. It gets worse if I cascade 4 of these filters. So if the respective super channel would have to go through 4 ROADMs in the end. And you see that the cascadation of several filters or ROADMs does not pose in quite a broad range of the subcarrier spacing an additional penalty for the partial response. So in real networks, it really seems partial response is a good thing to do. And that was 4 subcarriers in 125 gigahertz. And now, what if I'm after even higher spectral efficiency? So let's try to put them all into a 100 gigahertz slot. This is 400 gigabit in 100 gigahertz. Well, we didn't display, where is the laser? We didn't display the QPSK anymore because we couldn't. It has more than 10 dB penalty, it wouldn't work. Whereas, with a say lower number of cascaded ROADMs, the partial response would still go through the network. So this is quite an efficient possibility of gaining spectral efficiency. And think about what was partial response. It was just a little delay, tap, filter, and some additional filter in the transmitter. So that would be something that the transmitter now would have to provide as an option. And consequently, the whole thing may look like this. You saw the picture more or less at the beginning of my talk. Slight change here in the transmitter. So as compared to today's Coherent 100 gig, very, very, very likely the next generation will also see DSPs in the transmitter, because that is exactly required to provide this software definition. The receive end is more or less the same. Of course, there is some adaptation required or some additions required in the digital filter, but that's again software. And hence, this seems to be a pretty nice building block of next generation flexible software-defined transceivers. And the whole thing then would or could look like this. Take, for example, 4 of these. Every single one with an IQ modulator and its DSP at the transmitter, and consequently same thing here. And the DSPs may now provide for whatever QAM or QPR or other filtering. And by the way, they would also be responsible for how tightly the subcarriers are put together. So all of this is being made flexible. And then keep in mind that there is the relation of the payload or capacity that you get and the achievable reach. That SDO can't overcome. That is clear. We will not do transoceanic ultra long haul within the next decade or so on single carrier with 64 QAM or something. That's not what I talked about, but it gives you the flexibility to transport higher capacities over shorter distances. So it gives you some nice flexibility for ultra high speed transport. As I said, keep in mind the relationship between reach bandwidth and spectral efficiency. That is analog bandwidth, if you like. And yes, of course, we do see this as the solution for next generation intercampus transport. Thank you.
Thank you very much. We have roughly 5 minutes for questions. If you have any question, there is one in the, let's start in the front and then the gentleman in the back.
Well, as always, it was a complex talk. And so I'm not sure, I will just to understand, let's say, the major context. In addition to now in coherent detection, we have digital processors at the end of the line, and now you will introduce, or in near future, you will introduce, in addition, at the beginning of the line, another kind of digital processors to allow multi-modulation aspects. That's it? I mean,
yeah, short story, yeah.
That's
but that's what we definitely will see in 400 gigabit transport, correct? So
okay.
we need another DSP to get flexibility regarding the modulation scheme, the whatever I do with my subcarriers and additional filtering, etc., to get the respective flexibility, to in the end to be able to flexibly switch from, I don't know, BPSK maybe to QPSK to 8-QAM to 16-QAM to 9 QPR, whatever we want to do.
And I mean, did you do already experiments with that in ADVA, or is it just a concept? I'm not sure.
Well, it started with simulations, of course, and we are not the only ones, for example, who are thinking about partial response. Certainly, there is already lots of experiments with multi-carrier transport, and that's what we start now. Yes, so we are now in the phase of starting with experiments, which of course will be supported with simulations and all the other things.
Okay, thanks. And finally, is there a paper? Is there a paper about that?
Yeah, one would be our OFC paper of this year, and of course there is also a short paper and the respective slides here, and drop me an email and I can send you anything you want. I think there was another question here.
So, hello? Okay, so my question is about what sacrifices existing networks would have to make to gain this sort of flexibility. It's really clear to me that that the ROADMs would have to be flexible in terms of the spectral grid. But if you take existing networks that based on on-off keying, 10 gig type stuff, we've got great things like IP over DWDM, tunable interfaces in our routers, that sort of stuff. With these sort of flexible transceivers that you're describing, do you see that as technologies that will remain in transponders and muxponders within DWDM systems, or do you see some sort of standardization in the future for flexible systems?
Okay, I think there was a whole bunch of questions and or comments. The ultra high-speed transport, of course, will start, and it always did, with transponders. And the more technology advances, and by the way, I didn't mention it, but of course, the enabler of multi-carrier flexible optical transport is called integration or photonic integration or PICs or whatever you call it. That is for sure. And the more that one advances, the smaller the things get. And I guess in the end, we'll end up with pluggables that can again go into routers. But it effectively, and that's what I tried to say on one of the slides, it is the routers who are driving this. They have the one way or the other go for the 400 gig. It's not simply about increasing the transport, but they have to aggregate higher and higher capacities into single logical interfaces. So in the end, we will do see 400 gigabit pluggable router interfaces, sure. But in the beginning, they will not be long haul capable. So that is the one thing. It'll start with transponders, and the better the integration gets, and the more mature the technology, etc., the more it tends to become a pluggable. That's what we always saw. And the other thing, I guess, was the flex grid and certain other related aspects. Okay, to make networks to be deployed today, let's put it that way, ready for the next generation for 400 gig or so would mean deploy flex grid ROADMs. And also, as a very, very strong recommendation, don't compensate your links. Don't even think about combining it with on-off keying. Because on-off keying is what is now being called the aggressor. And it will stay like that in long haul. That's physics. That has nothing to do with us or Siena or Alcatel-Lucent. Also, an intensity modulated signal produces over effectively via the fiber nonlinearity that I talked about earlier. It produces phase noise, and so it's very likely if whoever can afford to do so, build an overlay network for Coherent only. and make it flex grid, because then it will support 400 gig or whatever comes.
Thank you very much again, Klaus. And we have the last speaker of the session, Rodney Wilson from Siena. Probably I can just close this security alert. So that was an alert that it's another company, it's not ADVA anymore. So the floor is yours.
Thank you. Good morning. My name is Rodney Wilson. I am not from ADVA. I am from Siena. My presentation this morning is really in 3 parts. The first part to talk a little bit about what Siena is doing in terms of research partnerships, why we participate with the research and education community. The second part is a retrospective of some of the work we've done and what we've learned through collaboration in research networks. And finally, a look to the future internet, some of the bandwidth problems, how we've solved them, and also look at control plane issues and provisioning capabilities in the future. So hopefully that meets your expectations. It's my pleasure to talk to you this morning. Excuse me. We often look at R&E as research and experimental networks, projects that we do collaboratively with members of this community. The graph is a classic marketing chart that basically shows how products or technologies are adopted in the marketplace. And our involvement is at the very thin edge of that adoption curve. We work with innovators and people that are willing to take risks and truly experiment. Now, the reason you do it at this location is because the consequences of error are not that great. If we work and something doesn't perform, there's not a lot of costs involved. However, if we had done it a lot later when the product was being highly adopted, and we found that there was an error in the design or a flaw, of course the consequences of replacing the technology, repairing the technology is very huge. So we do this work sort of beyond the product horizon. We participate in research activities, and we learn by doing. And of course, we're a vendor, so part of this is revenue development. But I'm in the technology organization, and we're really interested in discovering the future. This is a well-known map prepared by the Global Lambda Interchange Facility, or GLIF, and is excuse me, is designed primarily as a planning tool. It's also a planning tool for us, and we have an incredible installed base, both in terms of transmission systems as well as POPs and regional networks. The next part of my presentation really is a bit of a retrospective of some of the projects we've done, some of the work. Some of these were long-term joint activities that lasted many years. Some of them were simply proof of concept. Will it work? Won't it work? Use a testbed network. There are often things that we can do in the research network environment that are very difficult for us to simulate in the lab, and so we're always delighted to collaborate and use your testbeds. Some were demonstration networks, such as we've had here this week, and some were more simply product field trials to verify operation of new products. And in the spirit of research, some worked really well and some didn't work so well at all. So by way of retrospective, I'm going to take you on a very quick 10-year trip, going back to Siena and its earlier corporate configurations back to 1999. Much of what we've done has been focused at the supercomputer conferences in the United States, largely because these are also research events. More than a third of the participants come from universities or the NREN community. And there is an experimental flair to this meeting. I refuse to call it a trade show, although if you wanted to investigate high-performance computers and see what the new IBM Cray AMD computer looked like, I suppose you could go there. But for us, it's always been about the test bed. And in 1999, there was a special flavor of this test bed created called the XNet, the experimental network. And just to make sure that this is well and dated, the chart that you cannot read features ATM and an OC3 transmission capabilities in a collaborative test bed. But it outlined a lot of the early work and the spirit of collaboration that we've had for many years. So there's a shift, of course, in research and education networks. We see the demands to have a requirement to have content anywhere at any time, application-based performance, dynamic bandwidth allocation, some degree of protection in the network or protecting your network from students, and a need to differentiate services. Of course, in the network world, that means a highly reliable, latency-based routing or bandwidth on demand, and secure out-of-band signaling, or even optical VPNs. So some of the requirements of this community are reflected in the technical things that we try and achieve with our products. And so we have some examples over time. Bottom line, of course, is NRENs don't want dumb pipes. They require a lot more from their networks. And so historically, one of the first ways we did this was in 2001 for a long-term trial network called the OmniNet, which was based in Chicago. We developed all optical switches at the time. MEMS technology was very popular, so mechanical mirrors actually to steer light. Of course, now we use various grading systems and wavelength selective switches. But our purpose in this experiment was quite interesting because we wanted to take optical switching and see if it would scale to a metro environment. So we connected 4 university campus sites together with these switches. We also developed some very early digital optical compensation technology that later became a very important part of our 10 gigabit long haul technology. So it was foundational for a lot of work that we've done, turned out in our products, the electronic dispersion compensation algorithms, a distributed service plane, and answer the question, will a large carrier optical switch work in the metro environment? And for us, this was a fantastic success. It lasted for nearly 5 years. At the same time, of course, the industry did the telecom nuclear winter. People that built components went out of business. The fellows that understood how this was deployed at the university moved on. So these things have a finite life. One of the other projects that has produced some software that is still in use today was the DRAC, or Dynamic Resource Allocation Control. And its first appearance was in 2004. This is the father of DRAC, Franco Travestino, who's now a fellow with Apple Engineering. And the whole experiment was really to do a multi-domain secure call setup on demand without any operator intervention. So it was the application taking control of the network. And I mean, the basic message was, you may have solved the bandwidth problem, but are you getting good, efficient use of your infrastructure? And it was a fantastic collaboration with several NRENs around the world on 3 continents. So we also were able to accomplish a number of world's firsts. It was the first control bandwidth across multiple domains in a multi-vendor environment. It exploited the scalability and inter-domain fault recovery within the network. and really introduce sort of service-oriented architecture within a legacy control plane environment, and is one of our great milestones and successes. We took that and the following year really put it into a virtual environment. So we created a live machine migration where the application and the operating system would migrate. Now it's kind of an interesting experiment because we sort of set it up on the assumption that there was the application was going to be disaster recovery. And so we needed to simulate a disaster. So we had a little heat sensor and a hairdryer. You can see a little blue box there. So we put the hairdryer on the heat sensor to represent a fire in the data center, and the system sensing the temperature over temp would cause the network to go and discover a path, to provision the path, to migrate the operating system and the application. And in this case, we migrated from Tampa, Florida, which is where we were located, and we were able to migrate the operating system to Amsterdam and then a further trigger to Korea with KoreaNet. So we're working with SurfNet and KoreaNet in this way. The entire provisioning of the circuit from this perceived disaster through to a migration took less than 70 seconds. And like many of these experiments, we had a visualization, a movie, I don't know, it was Lord of the Rings or something, playing on a screen. And you could see that the application actually moved with the OS migration. So the 2006 demonstration of the virtual machine turntable really established some of these dynamic discovery and routing capabilities. 2008 was the first appearance of 100 gigabits per second in a long-haul production network. We worked with the Texas Learn regional NREN and basically built a multi-node infrastructure that was able to carry production traffic at distance over a production network. So the reliability had to be there, the trust had to be there. And I think a big part of what these collaborations establish between a vendor like Siena and a research network like you is this level of trust and collaboration. Would you have allowed me to bring an experimental 100 gig switch to your network and put it into production back in 2008 if I was a complete stranger and didn't have some of this history with you? Perhaps not. Last year, 2010, one of the research demonstrations we did was quite interesting. We put in place an upgrade of an existing 10 gigabit per second circuit, upgraded it to 100 gig between Ottawa, which is where I'm located, and our research and design labs there, and the Starlight Gigapop in Chicago. So this is actually a first 100 gig demonstration network of its type, distance of over 1,300 kilometers. But the real point of the exercise was not just to establish a link, and we did it in partnership with a number of different databases that were able to provide source data, but we also did it in collaboration with the Montreal Neurological Institute, a world-famous brain and neurological research organization. And they had a device or program they called C-Brain. A C-Brain, they took a human brain, sliced it 17,000 times, took ultra-high resolution samples of this, and make it available to researchers. Well, we're in Iceland, so if we were all neurological researchers, I suppose we could go to Montreal. But because we have these ultra-high-speed networks, we're able to access this, this research remotely. The resolution of the pictures, the nature of the interaction with the database requires ultra-high-speed connections. And in this way, research networks and these ultra-high-performance networks are actually contributing to research that improve the human condition. The project is called C-Brain, and if you Google that, they actually have a YouTube demonstrator of exactly how you can look at the human brain, but I won't go there right now. Last year at TNC, we kind of had a self-inflicted research question. And the question was, can you provide a 40 gigabit Ethernet connection through 37 different spans over a distance of more than 3,000 kilometers through 3 different national networks as a foreign or alien wave, and an infrastructure provided by not just Siena but multiple vendors? Oh, and would you do it at a public venue so if it didn't work, everyone could see exactly how well it performed? So we were up for the challenge. Of course, the big challenge for us was alien waves and looking at the power levels and some of the challenges in designing this network. In fact, we were quite successful. We created a circuit that ran from CERN in Switzerland through France, through Belgium to Amsterdam, then Amsterdam to SurfNet to Norgenet. Our original intention was trying to extend this all the way to Norway and Stockholm, but frankly, we ran out of time and engineering resources to accomplish this. So we terminated in Copenhagen. In effect, did a loop back and some interesting measurements on that. So we showed the results. The University of Amsterdam used this circuit for some latency experiments as they manipulated different protocols and so on. And so we were able to show these results on an iPad, which was rather cool at the time. Excuse me. Last year we also did an experiment for particle physics research. And it was an interesting discussion because, if we're looking at bottlenecks in the performance of networks, we know that one of the past bottlenecks was, of course, the hard drives, right, with seek time and little heads bouncing in and out around spinning platters. So we kind of solved that with solid-state drives. So then the network has traditionally been a bottleneck. So with the high-performance, long-reach, high-capacity networks, that was kind of solved. So the bottleneck actually turned out to be the bus architecture of the server. So with the high-performance NIC card from a company like Mellanox, they're able to create a long-haul testbed with the California Institute of Technology and the University of Victoria in British Columbia, and set up this testbed to try and find the new bottleneck. Well, it turns out that the bottleneck was, as I say, the bus architecture, but it was also the solid-state drives. They weren't able to write to speed yet. And this experiment is being recreated this week between CERN and Amsterdam with new servers, new server bus architecture, the PCIX3 bus, as well as some new components. And so we're waiting to hear actually today how these experiments perform this year. So the self-inflicted research question this year was make 2,300 kilometers of sea disappear and move Iceland closer to its Scandinavian neighbors, then do something cool with it. So the challenge we had was addressed through a large level of partnership with Norgenet, with SurfNet, with Far Ice, Netherlight, University of Amsterdam, the local service provider, Mila, and as I say, the submarine company called Far Ice. The wet plant that we upgraded to 100 gig runs about 2,200 kilometers between here and Copenhagen, and then links from the landing, which is an unmanned bunker about 3 hours drive east of here, and connect fiber through to this location here in Reykjavik. At the other end, to transit through Norgenet and SurfNet to Amsterdam to connect to the video servers that you've seen some of the images of this week. So we've done, in essence, 3 demos here. One is a transmission showcase to achieve a 4,000 kilometer link, including an upgrade of the undersea wet plant. The second is to look at some of the 4K video transmissions. The The images you see on the screen in our booth were simply not possible to present in Iceland in that way last week. So it really is a first appearance of this kind of video transmission in an uncompressed environment in Iceland. And the third experiment was actually a university project with the University of Amsterdam, where we're playing with different color frequencies of light and being able to select bandwidth specifically in a multicast environment. So we've had a great time and frankly a tremendous success that we're very proud of. And thank you, Tarina, for allowing us to stage this work here. And some images there. So the last part of my presentation, I'm going to look at where this research is taking us, some of the things that we're learning and how we're applying it longer term. In today's intelligent infrastructure, and my colleagues from ADVA presented some interesting views of this earlier, where I stand in Siena, we're really looking at intelligent infrastructure here in three ways. One is coherent and digital signal processing research. The second is packet optical switching. And the third is control plane. So these are the core technologies of intelligent infrastructure and very much the focus of Siena's work. Of course, there are other aspects to the total solution that are important to NRENs. But these core technologies are our expertise. Excuse me, I'm sure this cold will be gone by the time I leave Iceland. Klaus was talking in detail about the technologies that are needed in order to improve transport efficiencies. For us, we've got a very clear statement of work. A statement of work that is applied to our R&D and research partners. We need to improve the efficiencies by really doubling the network traffic and have a very forward-looking capability. The ability to deal with various distortion and nonlinearities, both for point-to-point submarine and high PMD environments. And of course, we need to improve the spectral efficiency, to look at new modulation techniques, to take QAM and apply it in new and novel ways, and also look at pulse shaping and flexible grid applications. And then, of course, we have to improve the operational economics. So new ingress and egress technologies, the ability to have contentionless, directionless, and colorless flexible grid applications in ROADMs, and to enhance the physical layer control plane to permit things like data mining, green ICT, and high-performance networks. So this leads to the next generation modem technology, and it has to enable more than 100 gigabit per second transport. There are three levers or three areas that we're working on to achieve this. One is to increase the bits per symbol, so to go to higher densities of QAM, to look at higher resolutions in analog and digital conversion, basically trying to do more gates per DSP, and also to come up with more efficient forward error correction techniques. As we've heard, one of the solutions is to go with multiple carriers to create an effective super channel, and this has the effect of making a very effective wavelength division multiplexer and coherent frequency selection techniques. So in order to increase the capacity, the other spectrum, of course, is to increase the number of carriers. And the third area is the ability to increase symbols per second, so basically a higher baud rate. And to do this, we need, again, faster analog to digital conversion. We need a greater density in our ASICs and our digital signal processing. We need much faster analog electronics, and we need high gain forward error corrections. So the statement of work that we've undertaken at Siena to achieve more than 100 gig really requires technical revolution, technical evolution in all three of these axes. And we've achieved it. This is a picture of the WaveLogic 3 long-haul 100 gigabit per second module in its native habitat. This will achieve a long-range submarine systems. Will certainly exceed 3,000 kilometers in 100 gig capacities. It's also the platform for speeds beyond 100 gig, and we'll see experiments and applications of this at future Torinos. The evolution on the switching side, on the hybrid switching side, looks at how this whole thing has evolved. So the cost and layers at 10 megabits per second, sort of circa 2000. We had very simple MPLS backbones, IP layer services, cost effective at low bandwidth speeds, and then branch to branch and branch interconnects. From 2005 to 2007, we see the emergence of VPLS and ELAN services. So Ethernet as a service layer became common. Bandwidths up to 10 gigabits per second and sometimes faster. Very cost effective at 1 gig. And in addition to branch interconnects, also introduced the ability to interconnect data centers. So this technology enabled new solutions that are very important in the R&E space. And as we look to 2012 and beyond, we see the arrival of optical VPNs, the ability to mix different environments, whether it's optical transport networks, OTN, SONET, or SDH control plane environments, to look at protocol transparency. So it doesn't really matter anymore which protocol you're using because it's an optical VPN. It has to be secure. We've introduced the provisioning technology in OpenFlow, and the points made earlier today about how this scales to layer 1 are very valid, and it's a very important piece of work. NNI is important as we look at flexible management techniques of these infrastructures, and the capacity is high, and the applications replace private networks. So if we put all this together in a single chart, we have enabled the solution that allows you to choose whether you need capacity, whether you need to minimize latency, or whether you need to maximize distance. And so you have 3 levers that you can operate around designing a flexible network. Across this, of course, we have a control plane technology that is able to analyze in real time the data requirements, determine the path impairments, and make specific route and link engineering recommendations. We can reset the path configuration to match the capacity or performance requirements that you need, and we can also mine the transmission data from the line, and in effect, your transmission system is also your test set. In fact, this is what we used here this week to determine the possibility of our upgrade of the submarine link. Rather than bring in analytical equipment, we were able to actually use the system to provide the diagnostics and fiber characterization information that we needed to optimize the system. So in this way, I've given you information about Siena's intention and work with the research community, a dozen years of collaboration, and a glimpse as to what's next and around the corner. So I thank you very much for your time. But before I end my speech, I'd like to recognize a friend and a colleague and a gentleman who is a tremendous asset to this community, Jan Willem Elion, who died last month in the course of setting up this demonstration and this work I've been talking about. He took a ski weekend and went to Switzerland skiing and died tragically in an avalanche. And we at Siena, of course, were devastated by this news. And I really dedicate our work here, our demonstration this week, and this presentation to the memory of my colleague, Jan Willemelian. Thank you.
So, is there any question to Rodney? If not, there is one question in the back.
Yeah, hello, Rodney. Thanks for your presentation. Quite nice. I have a question on your optical VPN that you mentioned. Did I understand it correctly that it's consisting of OTN, SDH, or Sonnet, and of the wavelength layer? So if yes, then my question would be, how is the interworking between the electrical switching layer and the optical switching layer there? Is it overlay or is it peer-to-peer? From a control plane point of view.
Okay, so you're very good at asking questions with layers, much like the network, right? The application of Sonnet and SDH is clearly a legacy protocol, and so for our carrier customers, it's important that we continue to support and feature these. The direction is very much towards OTN. We address it in a parallel architecture, so separately, if you will, we have a single platform that is able to deal with the multiple protocols. One of the applications of this technology is really carrier grade Ethernet or CESD capabilities. Most of our customers are in fact service providers and carriers, where this level of integration is perhaps not as tightly interleaved as we would see here in the research community, but nonetheless both solutions have to exhibit in a very economical platform. And we're just starting to see deployment of those platforms in research networks around the world. There are a couple of the gigapops that are using this both for optical Ethernet as well as OTN transport in a mixed environment.
Okay, thank you very much.
Thank you.
Thank you very much again, Rodney, for this.